Hello, Mr. Sorrentino here again. I'm doing another one of these videos for our Math 31 course. And this is the first section of the last chapter that this course covers, 6.1 Systems of Equations in Two Variables. When you deal with situations like this, essentially what we're looking for, when we want to solve a system of equations, as it states right here, the solution from a graphical standpoint is given by the coordinates where the two lines intersect one another. So if I would graph each of the lines and see where they intersect, that intersection point would be the solution. The issue is that there are some problems with graphing it, and we're going to see those a little bit in this part right here. Notice that I have a graph set up going from -5 to 5, both for the x's and the y's, and I actually have 1, 2, 3, 4, 5 spaces for each full unit. So this is basically going by fifths or 0.2s. So it's always a good idea to have an idea of what the scaling of your graph is, so that you have an idea of where you can place points a little bit more accurately when you actually get to graphing. But sometimes, no matter how well you try to prepare for that and make it as precise as possible, you may have a scaling that doesn't just work really well with the equations. Case in point, right now both of these equations are linear equations. They're written in more of the standard or expanded format. And so for me to graph them, and as we've done before, we also put on the graphing calculator, even to do that I had to solve for y. When I solve the top one for y, I get y equals -4/3 x minus 2/3. This graph is not set up to go by thirds, it goes by fifths. So, 2/3 is about 0.66666 repeating. So somewhere between 0.6 and 0.7. And so I could probably say for -2/3, going by fifths, so I'd go down 1, 2, 3, that'd be 0.6. Next would be 0.8, 0.7 would be somewhere in between. So maybe roughly somewhere around here. But that's a speculation, that's a guess. I can't say for certain, that I'm doing this exactly right. I might be off a little bit. And then I could do the rest of the points, which means if I follow the slope, I go down 4 and right 3, or I could go up 4 and left 3. I might want to do a little bit of each. If I go by full units, it might be tough. But since the x and y scales are both going by fifths, I could count this little boxes as well and say, okay, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. That gives me nice 3 points here. So there was some guessing I had to do for this one because of the fact that this graph isn't really scaled to go by thirds. On the other hand, the second one, if I were to write this in slope-intercept form, I would have y equals a positive 2/5 x minus 12/5. This is a little easier to graph because my graph is going by fifths. So I could say, okay, down 12/5, I just have to count 1, put it here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12/5 would be here exactly. So sometimes it does work out for us, sometimes it doesn't. So here's the point here. And again, since my x and y axes are scaled the same, I could use the small blocks I have in here when I use my slope of 2/5. I could also go up 2 full units, right 5. I just don't have as many points that way. So I'm going to do 1, 2, 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5. I'm going to pull out the ruler again. Now, if I graphed it right, it looks like right here is where they intersect. It looks like it intersects at 1, -2. And I can actually confirm by either plugging those coordinates in, 1, -2, or using the calculator. It says I can confirm by plugging 1 and -2 in for x and y respectively, and seeing it does work for both equations. I'm not going to do that in this video. You're welcome to do that to do your own checking. Or I could also check it on the calculator just to briefly go through that. So I'm starting off now. These are the equations I got when I solved for y and put it in the slope-intercept form. And so if I would graph them, and I set up my window to be very similar to this, going by -5s. I'm not going by tenths so much. I don't want to see too many like dots on my axes. As long as I have the min and max the same, the scaling doesn't matter quite as much since the calculator can actually do calculations of that matter. And I'm going to graph it. It looks like 1, -2 is the right answer. I can verify that by going to my calculate menu. And like I had done in the problems prior in this course, I can find where these two graphs intersect each other. Now with lines, it's pretty easy because they should intersect at one point if they do intersect at all. So I'm just going to choose the line, choose the line. I don't really have to guess. I mean, if I want to, I could perhaps move this closer to what the intersection point is, but it's not necessary. Like you can see, I get the intersection to be 1, -2. So that verifies the solution to it. So now, but as I mentioned before, it didn't happen so much in this one because of the fact that, it's not going to be way off, but sometimes the scaling of your graph might make it difficult to graph as exactly. And what if the solution isn't meant to be, integer coordinates? I mean, I could have, fraction coordinates or even irrational coordinates if necessary. Probably won't see that much with linear equations, but it's possible. So graphing can be difficult because your graph may not be completely able to show the answer as accurately as you need to see what the right answers are. So we use algebraic methods, which is what the main focus of this particular lesson is going to be on. But we also have to be aware that we have situations like this where we have lines that intersect in one point and therefore we'll have one and only one solution. There are two other circumstances, special circumstances, that do pop up from time to time and you need to be aware of. And on page 2 of your notes, we do mention these two other circumstances. A situation like the example we just did is called consistent and independent. That means I have one and only one solution. That's what the consistent and independent mean. One and only one solution. And lines often will intersect at one spot, but they also could do two other things. I could have the lines be parallel, which means they would never intersect, which means that there's no solution, and we would call that inconsistent and independent. Now I can see that graphically really easily. The question is, how would I see this algebraically? We'll look at that momentarily. I could also have two lines overlap. If it's written in slope-intercept form, and if you simplified all of your fractions, it would be very noticeable because you would have the exact same equation. But if they're written in an expanded form we saw in the example, it may not notice it right away. It's going to tend to happen, and something happens in the process of solving it algebraically. It's going to let you know that as you do it. But we can have that situation where all points on one line are intersections, so they're infinite solutions. We would say that's consistent and dependent. So basically the line itself is the solution because there's a bunch of ordered pairs that would make that work. It doesn't mean every ordered pair. All points, and I should say really here, emphasize on the line, are solutions. They're all intersections too, but so there's infinite solutions. I have to be able to be aware of those two cases as I do my work for these and recognize them when I see them. So let's start looking at the two methods that we do make use of as we solve this. The first one is going to be substitution. The two methods that we have to solve, as I mentioned before, are substitution. The other one's going to be called elimination. Sometimes they call that linear combinations as well. So if you ever see a direction, although it shouldn't happen in this course, but in future courses you're asked to solve a system of equations using linear combinations, it's the same thing as elimination. But substitution or elimination, it doesn't matter which one you use. There are some circumstances that are better equipped for substitution and others that are better equipped for elimination. You could use them interchangeably. You could use them, based on the situation, on your decision making. You could choose to use one only or the other one only. It doesn't really matter to me which one you use, as long as you're using a correct method and make the right conclusions when special circumstances arise too. That's all that concerns me. So, but essentially, substitution works best under part A, as you see here. I have one of the equations already solved for one of the variables. When I have a situation like that, that's really set up to do a substitution. Because what's going to happen is, if I didn't have the equation already solved for y or x, whichever the case I choose to solve it for, and it's usually your choice as well, I'm going to solve one of the equations for one of the variables, and then I'm going to go to the other equation, and I'm going to perform that substitution. So if I'm just going to rewrite this as 6x plus 2 times y. Now y is now negative 3x plus 1. So I rewrite the top equation, replacing y with what it equals in terms of x. And so now I carry out the algebra. I want to solve this equation. So we're going back to the things we've done earlier in this course. So I'm going to have 6x. When I distribute the 2, I'm going to have a minus 6x plus 2 equals 7. If I simplify any more, and here's what goes on with this one, that's a little alarming. Both variables disappear because 6x and minus 6x will cancel. I'm left with a statement 2 equals 7. So the very first example we have here is going to give us a special circumstance. Let me put an asterisk there for this. Anytime that you're solving a system of equations, whether you're using substitution or elimination, if both variables basically disappear in the solution process. Now, it shouldn't happen all the time, but there are going to be problems there where it's going to happen. If both variables disappear, then I have a special case. Hence, I'm putting the asterisk here. The special cases are the two things that were mentioned before, having either no solution or an infinite number of solutions. The question is, what information do I have here that'll let me know which one of the two it is? Because everyone thinks automatically it's going to be no solution, no solution, no solution. In this case, it is no solution, and the reason why is because this statement that was left is false. 2 does not equal 7. So that tells me it's no solution. If I were to graph these lines, I would see that they're parallel. And so, using terminology, they're inconsistent. Now, they're not asking for the terminology. You will be asked for it. We don't usually say inconsistent and independent. The independent means I would see two separate lines. The inconsistent means that they're not going to intersect anywhere, so that's the inconsistent part. Inconsistent automatically assumes that they're independent of each other. So that would be an instance where I have no solution. In B, one of the things that sometimes causes students difficulty with this is that you have many different alternatives to do and choices to make as you do this. And obviously, if I'm going to use substitution to solve this system of equations, I have to first pick, okay, which equation am I going to solve for one of the variables, and which variable am I going to solve it for? Technically, theoretically, I could solve the top equation for x or the top equation for y. It doesn't matter. I could do the same thing for the second equation. I could solve it for x or solve it for y. The choice that I tend to make is based off of, well, what's the easiest of them to do? Which one requires the least amount of steps? If I solve for x or y in a top equation, I'm going to have to carry through a subtraction on both sides and a division and get some nasty looking fractions as a result. So I'm going to have decimals involved or fractions, and that could cause some grief. Same thing if I were to solve the bottom equation for y. I would have to subtract the x from both sides and then divide both sides by 2, which would bring about fractions in it. The fact that I have, this x with nothing in front of it is what would lead me to say, okay, I'm going to solve this one for x. And it only takes one step. X is negative 2y plus 11. So I have that set up to do my substitution, so I go back to the first equation. Now, as I said, is it wrong for me to solve the bottom equation for y instead? No. Is it wrong for me to solve the top equation for x or y instead? No. It's just a little bit more complicated, that route. And so, I often make the choice based off of which one's more or less complicated. I'll tell you with all honesty, this is one I might have usually chosen to do elimination on. But substitution is not too bad for this one either. So I'm going to go to the top equation. I'm going to replace the x with negative 2y plus 11 plus 5y. Everything else is being left alone in the top equation. I'm just replacing what the x is. When I distribute the 3, I'm going to have negative 6y plus 11 plus 5y equaling 31. Oh, take that back. This should be 33. Negative 6y plus 5y would be negative y plus 33 equals 31. Negative y, when I subtract 33 from both sides, will give me a negative 2, which means y would be 2. Now, with this, I know what the y value is. The easiest thing now to do is to come back up to here, to the x equation, and substitute in for the y. And so when I do that, x equals negative 4 plus 11, which means that x is going to equal 7. And so oftentimes you're going to be asked to write that as an ordered pair. Because remember, this is representing the intersection point of these two lines, but it's also telling me the x and y that makes both true at the same time. And again, this would be an instance of being consistent and independent. So you can see how this works, although when I circled this over here, my 7 kind of disappeared. And I could see how a special case can show up and how to make the conclusion. When I do elimination, which is the other method that we make use of to solve a system of linear equations, and the one I most often use. So when I solve equations using elimination, what I am going to try to do is I want to take, first of all, it's going to be in this expanded form. And I do want my x's and y's to line up. So if I have, an equation that starts with an x and goes to y equaling a number, and I have another one that starts with y and then the x equaling a number, I want to rearrange and make sure I keep the signs where they belong. Rearrange it so that my x's and y's line up. And when we do other solution methods as we move through this chapter, it's going to be very important to do that for other reasons as well. And we'll talk about that when we get to those. For elimination, and the reason why it's also known as the linear combination method, is because if there's a true solution for both of these equations in A, if I add them together, I would get yet another equation that should share the same solution. So, that could be very helpful in some cases, but, if I have another one that just has an x and a y term in it, it doesn't really help me a whole lot. And that's because all I'm going to do is have a third equation that has the same solution, but not really know how to get to that solution. Ideally, what I want to be able to do is add the two equations together, combine the two equations, and have one of the variables disappear, cancel out, go away. So I can do some manipulation of this to make that happen. So what I usually have to do is I have to choose a variable that I want to eliminate. And then what I want you to do eventually is get the same number in front of that variable, but have different signs. And again, I make the choice about what I do based off of what's there and which would be the easiest to get to that situation where I would have the same number in front of the x's, with one being the opposite of the other, or the same number in front of the y's with one being the opposite of each other. So there's different ways you can go, but oftentimes there's going to be one that's a little easier than the others. So for instance, I notice that, well, I have a 4 in front of the x and a 5 in front of the x on the second equation. These don't have any factors in common. They have multiples in common. I could say, okay, well, if they're both 20x, I can go through and solve this and so forth and so on and make the appropriate adjustments. But, I had to alter both equations. Not that it's wrong to do so. It's just more work than necessary, because if I look at the y's, I have a 3 in front of the y on top and a 6 in front of the y on the bottom. 3 is a factor of 6. I also notice that the y's also have opposite signs, whereas the x's were both positive. And if I have both being positive, I'd have to multiply one by a negative, and I had to choose which one it is, and then make sure I'm distributing that negative correctly. So usually, if you're choosing a method that has more steps to it in the setup process, you are creating a circumstance where you have more opportunities to make errors. And so that's why I usually recommend trying to find the one that requires the least amount of work to do. It won't be wrong if you go another route. As a matter of fact, there will be some systems of equations that you have to alter both equations if you're using elimination, or if you choose to do substitution. You're going to have some nasty fractions in it, and you have to deal with it. So what I'm going to do is I'm going to take the top equation, and I'm going to multiply it by 2 so that I can change the minus 3y eventually into a minus 6y. Now the thing is, I just can't change the y term. I have to change everything. I have to multiply both sides in their entirety by that 2. In the second equation, I'm not doing anything to it. And so when I get my new system, since I'm multiplying both sides of the top equation by 2, I'm still making it equal. I'm making yet another equation that's going to have the exact same solution, but this one will combine better with the 5x plus 6y equaling 8, because I'm going to have 8x minus 6y equals a negative 18. And here I'm going to have 10x plus 6y equaling a negative 8. And I don't need to change the bottom one. I got multiplying by 2 happy. That stays the same. And so when I add the two equations together, 8x plus 5x is 13x. The minus 6y and the plus 6y cancel, and they should. Something should cancel. If you didn't get anything to cancel when you're adding the two, when you get to the step of adding the two equations together, then you haven't set it up correctly. One of the variables should cancel. And remember that for them to cancel, they have to have opposite signs. I will have students that will get a plus 6y on top, and then they'll say, when I add them together, they cancel. Well, no, if you add plus 6y and plus 6y, it's 12y. So make sure your signage is where it's supposed to be as well. And this is going to equal negative 18 plus negative 8 is a negative 26. When I divide both sides by 13, I get x is equal to negative 2. So I got my first value for one of the variables. Now what I do is I go back to one of the original equations. It really doesn't matter which one it is. I chose the top one. And I'm going to say, okay, I'm going to have 4 times negative 2 minus 3y equals negative 9, which means I have negative 8 minus 3y equaling negative 9. Adding 8 to both sides, I have negative 3y equals negative 1. And dividing both sides by a negative 3, I would get 1/3. So my solution is negative 2, comma, 1/3. And 1/3 might have been one that if you were graphing it, you wouldn't necessarily pick that as being the answer unless you happen to be plotting things by thirds and having a scaling by thirds. You may not have noticed that. You might, and of course, this is consistent and independent. Part B, I don't have a situation where one of the coefficients on the x is a factor of the other, and the same thing with the y's. So I'm not going to be able just to make one change to one of the equations, and that's it. I'm going to have to change both equations. What I chose to do is essentially, I chose to eliminate the x's. So I like to get a 12x in front of each one of them, and one of them I like to be negative. So I chose the bottom equation for that to happen. So what I did when I set this up is I said, okay, the top equation, I'm going to take 4 times the 3x minus 6y equaling 9. And I did negative 3 times the 4x minus 8y equaling 12. Remembering that I had to multiply this by the 4 and this by negative 3 as well. I almost forgot to write that. When I carry through the stuff on the top, because I want to simplify my system before I start trying to solve it, I have 12x minus 24y equaling 36. On the bottom I have negative 12x plus 24y equaling a negative 36. When I add these together, my x's do cancel. Great. But so do my y's. In actuality, so do the numbers I have on the right-hand side. So essentially, on the left, when I carry through this addition, I have nothing. On the right, I also have nothing. This is a special case. Both variables disappeared. So I know I have a special case. That's how I know. This statement, compared to the one we had in example 2 with the substitution, this is a true statement. True. 0 does in fact equal 0. And so if I get a situation where I have to conclude that there is a special circumstance and I end up with a true statement, that indicates that I have infinite solutions. And that means that I would say this is consistent and dependent. Essentially, the two equations I have are of the exact same line. Therefore, they're going to intersect each other everywhere. And so that's how you go through these two processes. So we have this word problem now for example 4. Dawn works for a computer store which sells Macs and PCs. She earns, on average, a $100 commission for each Mac she sells and $135 commission on each PC she sells. During the last month, she sold 26 computers for a total of $3,090 in commissions. How many of each type of computer did she sell? So, ultimately what I'm looking for here is I want to come up with a system of equations that I can solve to answer this. So I'm going to show how I usually go through and dissect a problem like this so that maybe you can mimic it and try other ones in the same way. But it does take information about reading it and making sure you know what it is information you got versus what you are looking for. Ultimately what we're looking for here is how many of each type of computer that Dawn sold. M is going to equal the number of Macs sold, and P is going to be the number of PCs sold. You can make them X and Y, you can make them any letters or symbols you want as long as you know which one represents which. So let's take a look and see what information that we have here. There's two things that we're looking for, because I mean there's only two types of computers they're mentioning, and they're looking for how much she sold of each. So I have two values I'm looking for, which means I need to come up with two equations that relates these two together. So one equation is the fact that she sold 26 computers were sold. That means that the number of Macs that she has plus the number of PCs that she sold should total 26. The other one is kind of split up in several different spots. So let's have a look at it. It has to do with her commissions. She earned a total of $3,090 in commissions. Put the total here. She has a $100 commission for each Mac and a $135 commission on each PC. So if I want to figure out how much of a commission she earned on the Macs only, I would take 100 times the number of Macs she sold, which in this case is M, because we don't know what it is yet. So 100M would be how much money she earned off of the Macs that she sold. Whereas 135p would be the amount of commission she earned from the PC she sold. And obviously those two values together should total the 3,090 that she actually got with the commissions. So there is our system of equations. So now, how do I go about solving this? Now, you could have solved it any different number of ways. It doesn't matter which way that you chose to do it. You could choose to have done elimination. I'm going to choose to do substitution. The top equation would probably be the easiest to solve for one of the two variables, so that's the one I'm going to solve. It wouldn't be wrong if you tried to solve the bottom equation for one of the two variables if you also chose substitution. And it's just as easy for one of the variables than the other, so doesn't matter which one that you would choose in this one as far as ease goes. I chose to solve for p. And so I changed this equation here into p equals 26 minus m. Because now what I'm going to do is I'm going to use this and substitute into the bottom equation now. So coming here and coming here, when I rewrite the equation, I'm going to have 100m plus 135. I'm going to replace p with what it equals. P is being replaced, equals 3090. I'm going to simplify this equation before I start trying to solve for m, because I want to get m alone on one side. So I'm going to distribute the 135. 26 times 135 is 3,510 minus 135m equals 3,090. 100m minus 135m is a negative 35m plus 3,510 equaling 3,090. Now I have m, I have one variable m now, so I can use the rest of the basic equation solving techniques. I'm going to subtract 3,510 from both sides, and I'm going to get 35m equals a negative 420. And then when I divide both sides by negative 35, I get 12. So she sold 12 Macs, which means now, if I come up to this equation again, that's going to be 26 minus 12, which equals 14. So based on the information that we were gathering here, and now we go back and make sure, am I answering the question that they asked for? Sometimes they may ask us how many PCs did she sell. They might ask how many of the other ones she sold. In this case, they're asking for both. So answer the question that's always given. Dawn sold 14 PCs and 12 Macs last month. And that's how you go through and do it. So with 6.2, the systems of equations in 3 variables. Although they should probably say 3 or more variables, because I think they do try to throw a fourth, 4 equations with 4 unknowns situation at you in some of the homework problems. Because basically the procedure that we used in the first lesson in chapter 6, these methods work with also system of equations where I have 3 variables with 3 unknowns, you know. And so basically, as long as I have the same number of equations as I have unknown values, I'm usually pretty good and either going to be able to find that they do have a solution in common, or that they don't. You know, they don't have a solution, or may have infinite solutions. Who knows? One of the issues tends to be, though, as we try to solve systems of equations at three variables, we don't have the option of graphing them because it would be a three-dimensional line graph, which is kind of hard to do on two-dimensional paper. Although some TI-84s may have the three-dimensional grapher feature on it, it's not necessarily going to be very useful, and it doesn't really have a tracing function anyway. So you would be out of luck to use that to find the intersection point, other than following along and seeing what the coordinates are. So we would have to use algebraic methods. It's just that they're more time consuming the more variables you have to solve for. Because when I look to do situations like this, there might be some substitution I could do along the way, but you're going to see more often than not that elimination tends to work best for this because of the fact that I'm going to have to get rid of one variable at a time. So I'm going to have to choose a variable to eliminate and then get equations written with those two variables, with that variable eliminated and the two others left, and then go through and do procedures to eliminate a second variable and solve for the one that's left. As I go through this, I'm going to note these equations as equation 1, equation 2, and equation 3. When I look at my x's, my y's, and my z's, I see that the y's, two of the y statements have a 1 in front, some of them with opposite sign, negative signs, one with a positive. The other one has a 3 in front of it. Whereas I look at the other ones, the x's wouldn't probably be too bad, 2, 4, and 1. I could probably deal with those if worse came to worse. And if I was dealing with the z's, I'd probably have a little bit more issues with those because although the 2 and the 4, the 2 does go into 4, 3 doesn't go in either one of them, and 2 doesn't go into 3, so there would be some more work to do if I tried to eliminate the z's. So I chose to eliminate the y's. So I'm going to eliminate the y first. For me to do that, I'm going to have to do combinations of two of these equations at a time. So I'm going to have my first one be 1 and 2. I'm going to try to start going through and solving that system. And the other one's going to be 2 and 3. If I take the 2x minus y plus 3z equaling 7, and the 4x minus 3y plus 2z equaling negative 2, and I make that my system. Well, for me to eliminate the y's, I want to get the same number in front of the y's with opposite signs. And I can accomplish that easiest by multiplying both sides of that equation by a negative 3. That's going to give me a plus 3y on top and a minus 3y on the bottom. They will cancel. But remember, I just can't change the one variable I'm looking for, and that's it. I got to change the entire equation accordingly. And so this equation, this system, is going to become a negative 6x plus 3y minus 9z equaling a negative 21. This one's going to become 4x minus 3y plus 2z equaling negative 2. And then when I add these two together, I get a negative 2x. The y's cancel as designed. Minus 7z equaling a negative 23. And if I want to make it a little bit nicer, I can get rid of all the negatives just by multiplying both sides by negative 1. And I would get 2x plus 7z equals 23. Now that's not usually what we're used to getting to when we do elimination. We're used to getting a single variable equation and I could solve it and figure out what the number is. But remember, I have three different variables I have to account for here, so I'm taking care of getting rid of the y's on this one. So I'm going to call this one here equation A. This equation is yet another equation that should have the same solution as the first three did. So whatever equation, whatever values x, y, and z are supposed to be, and whatever solution they're going to have, this one should have the same one as a solution. When I do 2 and 3, now remember, we're here to eliminate the y's again. So we're still eliminate y's. And the best way for me to do that, the easiest, is to multiply both sides of the equation by 3. I already have opposite signs on the y's. I just need to get a 3 in front of that y. So my system for this one becomes 4x minus 3y plus 2z equals negative 2. Nothing happened to the top equation. And I'm going to have 3x plus 3y minus 12z equaling a negative 21. And when I add them together, I get 7x. The y's cancel again. They should. That's what I was designing it to do. Minus 10z equals a negative 23. And I'm going to call this equation B. So I took the situation that I have now, where I had 3 equations with 3 unknown variables, and now I've come up with 2 equations with only 2 of those unknown variables that would have the same solution as those. So what I need to do now is take A and B together, and I want to solve this system. Neither one of them is particularly good for substitution. I would start getting, some decimals and fractions that wouldn't be easy to work with. I'm going to still choose to do elimination, although that's not going to necessarily be much easier because of the fact that 2 does not go into 7, so, and they don't really have any common factors, so if I'm going to choose to eliminate the x's, I'm going to have to change both equations. And if I do the same thing with the z's, the only thing I would possibly save in the long run is multiplying one of them by a negative, because I already have opposite signs on the z's. But since that's the one that's going to be probably the least complicated, I chose to leave the signs alone, and I chose to eliminate the z. The top equation, I'm going to multiply by 10, and the bottom equation, I'm going to multiply by 7. And so when I do that, I get 20x plus 70z equals 230. The bottom equation becomes 49x minus 70z equaling a negative 161. When I add the two equations together, 20x plus 49x is 69x. The z's cancel, as they should, because that's what I chose to eliminate. 230 plus a negative 161 is 69. Dividing both sides by 69 means that x equals 1. So I got one of the variables solved. Now what I'm going to do is come back to either one of these two equations, the A or the B. Since I have x and z only, I could put the x in and figure out what z is. So I chose A. So substituting in for x, I'm going to have 2 times 1 plus 7z equaling 23. So 2 plus 7z equals 23. Subtracting 2 from both sides, I would have that 7z equals 21. And dividing both sides by 7 would mean that z is 3. So now I know the value for x, I know the value for z. Now I have to go and figure out what the value of y is. And so I go back to up to one of these original 3 equations. Doesn't matter which one I choose. I so happen to choose the very top one. 2 times x, which we now know is 1, minus y, which is what I'm looking for, plus 3 times z, which we know is 3, should equal 7. So I have 2 minus y plus 9 equals 7. So 11 minus y equals 7, which means y would equal 4. So my solution, which we'd write as an ordered triple, and always alphabetical order, so x, then y, then z. And that'd be the solution for this. Or of course you could just indicate these, just make sure that you indicate what they are. Maybe even summarize it and put it all together, but that would be your solution. So you could see this takes a good bit of strategy. It takes a good bit of thinking your way through it, making decisions, and it involves a good number of steps. If there are methods that have less steps, it would be better to learn them, because if there's more steps, there's more chances of just making just some random computational mistakes, But of course, obviously, if there's methods that require less steps, that requires you to know different methods. So, so it's a give and take here. And most of the rest of this chapter is going to be dealing with ways for you that are less involved in this, or at least less overall steps that have to be taken to solve a system of equations like that have 3 variables or more. So let's have a look at the word problem. Casey receives $190 per year in simple interest from 3 accounts she has. So we're not going with exponential or compounded interest, we're just doing simple interest. The 3 accounts pay 2%, 3%, and 4% simple interest respectively. Casey had 3 times the amount of money invested at 4% than she invested at 3%. Find the amount of money invested in each account if the total amount she invested is $5,875. So the first thing here, we want to find the amount of money invested in each account. There was 3 accounts, so I'm going to let x equal the amount of money in the 2% interest account, and of course the others are going to be. So what we need to do is come up with 3 equations that relate these 3 unknown values together if I'm going to have any hope at all of solving this system. The first one I'm going to write here is the total amount she invested is $5,875. That's the easiest one there, because the total amount she invested would be the sum of these 3 accounts together, the original values of each one. So that means that would be x, y, and z added together. So that system of equations from that information would be x plus y plus z equals 5875. The second one I'm going to deal with and write an equation for, it tells me that she earned $190 per year in simple interest from the 3 accounts, and we know what their amounts are. Well, for me to calculate the interest she earned in each account, I would take x times 2% of that, and that'd be the interest she earned in that account. And for y, I'd take 0.03 times the amount she invested there. And then, the third account, take 4% times the amount she invested there to find their respective interests, and I would add them together. So that means that 0.02x plus 0.03y plus 0.04z is going to equal $190. So again, each one of those terms is the amount of interest she earned in the respective account, and then you take the amount she earned in each account, add them together, you get 190. So that's where this one comes from. The last one comes from Casey had 3 times the amount of money invested at 4% than she invested at 3%. So that means they're telling us a relationship between the variables y and z. X has nothing to do with that statement. They're not mentioning the 2% account at all, so they're saying she has 3 times the amount of money invested at 4% than she did at 3%. That means that the amount she has at 4%, which is z, is equal to 3 times the amount she has invested in the 3% account, which is y. So we know that z equals 3y is the third equation. There's my system. And to rewrite them, because maybe I don't like having the decimals so much in the second equation, I can multiply the entire equation by 100 and get 2x plus 3y plus 4z equals 190 with 2 more zeros, so 19,000. And I just multiplied both sides by 100. And z equals 3y. So there's my system of equations for this. So let's move over a little bit. Now we want to solve this. Again, as I go through and show how I went about doing it, your method may not have been exactly the same. So you might need to check through to make sure you're checking your calculations and everything along the way. But what I chose to do first, this made getting down to one variable really easy. I chose to use the fact that we had an equation that said z equals 3y. That means I could basically eliminate the z's from the two equations up there. So this one can be rewritten as x plus y plus 3z equals 5875. This one could be rewritten as 2x plus 3y plus 4 times 3z, or take that back. I should just say 3y. I think I said 3y and wrote z. 4 times 3y equaling 19,000. And so when I simplify these two, I'm going to have x plus 4y equaling 5875. And I'm going to have 2x plus 4 times 3y is 12y. 12y plus 3y is 15y. That's going to still be 19,000. So this is the system of equations that I have to solve here. If I want to use substitution, I could solve the top equation for x pretty easily without getting any weird fractions or decimals involved that could complicate my calculations. Even with that though, it's also pretty easy to use elimination to eliminate the x first and solve for y. And I could do that simply by multiplying the top equation on both sides by -2, because that would make the top a -2x, the bottom would have a positive 2x. When I add them together, they would cancel out. And so my system would become -2x minus 8y equals a -11,750. The bottom equation was untouched with my methodology. Again, if you chose to go different routes, that's fine. Just sometimes you might give yourself more computations to do as a result. So when I add the two equations together, the x's do in fact cancel out. That's what I wanted them to do anyway. When I add these two together, I get 7y. And this here, I get 7,250. When I divide both sides by 7, I get approximately $1,035.71. Now I could use the fact that z equaled 3 times y and just multiply that by 3 to get that z is approximately equal to $3,107.14. And then I could use these two values along with this equation and come up with that x plus $1,035.71 plus $3,107.14 should equal $5,875, which would be X plus $4,142.85, equaling this. Subtracting $4,142.85 from both sides, I get that X is approximately equal to $1,681.15. And so my final statement to answer the question based off of this information would be this. So she invested $1,681.15 at 2% simple interest, $1,035.71 at 3% simple interest, and $3,107.14 at 4% simple interest. 6.3 Matrices and Systems of Equations. So in 6.1 and 6.2, we learned methods of using elimination and substitution to solve systems of equations. When I have two equations with two unknown values, that's not a big deal. I mean, it works pretty well. I can make good decisions really quickly. When we try to use a similar process of elimination and or substitution, when I start getting three equations with three unknown variables, or even if we were, God forbid, given four equations with four unknown variables, or even more than that, the process of using elimination and substitution would be much more lengthy and time consuming as a result. So there are other methods to solve a system of equations in a little bit more of a streamlined fashion. And as we move through these subsequent chapters, we're going to learn different ways of dealing with this. And so we use matrices as a method of doing this. And I don't have a kind of formal definition of it, it's in your textbook, but an augmented matrix is basically me taking a system of equations, like A. Now I want to make sure, as I do this, I'm going to put a couple little formatting things down here. One, I want to make sure that the system has variables lined up. That means I want to be able to see, like, a solid, column of X's, a solid column of Y's, a solid column of Z's, all lined up underneath of each other. If I don't have that, I really should maneuver things around first to make sure that's happening. Now in A, it happens to be the case it is happening. The second thing I do is I write the symbol down for an augmented matrix, which an augmented matrix is going to have brackets, and I want to make these are going to be bigger to have enough room for these numbers. And I have a vertical bar in the middle of it. So it's going to be much bigger for this because I'm going to basically make this take the place of this equation, or system of equations, I should say. The left side are the coefficients only. So the 2 and the 4 here, the 3 and the -5 here. And then of course the right side are the results, or essentially the numbers that the equations are set equal to. So 5 and -1. And basically this lets me know that I have an X column and I have a Y column, and I have, of course, my result column. For part B, now one of the things again to pay attention to is the very first thing. You have to make sure that your system of equations is lined up. So I want to have an X, a Y, and a Z column, so I want to be able to see them. This one has them in this order, And so does the second one. I have my x term, my y term, and my z term. The third equation, if you notice, doesn't have a y term, and the z term is coming first. So I really should rewrite this as negative 8x, because that negative is attached to the 8x term, not the 2z, plus, I don't have a y term, but I can think of it as being plus 0y, and I do have a positive 2z term. And so this would be a good rewrite for my system of equations in order to come up with the augmented matrix. The augmented matrix for this would then be 2, 4, negative 8, making up my x column, negative 1, 3, and 0, making up my y column, 4, negative 1, and 2, making up my z column, and my results column would be 12, 3, and negative 2. And so that would be the augmented matrix for part B. So that's usually the first step if you're going to use one of the methods of using matrices to solve a system of equations, is that you're going to rewrite the system of equations as an augmented matrix. What you do next, it depends on which type of elimination you're going to. It's considered an elimination process, and you're going to see it has some similarities to some of the things we did with elimination. It's just a little bit more directed in how you should carry it through. The first one we're going to talk about is Gaussian elimination. So let's see what that involves. Gaussian elimination is a set of steps that we perform to our augmented matrix until it reaches a certain structure that allows itself and lends itself to us knowing what the solutions will be for the system of equations. Now, I do this by performing row operations on my matrix. As I do row operations on my matrix, I have to keep in mind there's only certain things I'm allowed to do. When I do row operations, I can interchange any two rows. So if there's, and we're going to find out how do we know if we want to do that or not, but I can interchange any two rows. So I have to make sure I do that in their entirety. I can multiply an entire line by the same non-zero constant. I never want to multiply anything by 0, because if I have a row of zeros or a column of zeros, that could cause some major problems and actually could create situations where I have maybe no solutions or infinite solutions in a situation where I really only have possibly one. So I want to make sure I can multiply an entire line or an entire row by the same number. And the third thing I can do is that I can add a non-zero multiple of any row to another row. These row operations make up, both Gaussian elimination and what they call Gauss-Jordan elimination. Gaussian, the only difference between the two is what kind of structure do you want your augmented matrix to look like before you say, okay, I'm done, I can start figuring out what the answers are. And here's what I mean. With Gaussian elimination, my goal is to convert the augmented matrix into row echelon form. In row echelon form, this is how they have a verbal description of it. If a row does not consist entirely of zeros, then the first non-zero element in the row is a 1, called a leading 1. For any two consecutive non-zero rows, the leading 1 in the lower row is farther to the right than the leading 1 to the higher row. All the rows consisting entirely of zeros are at the bottom of the matrix. If a fourth property is also satisfied, a matrix is said to be in reduced row echelon form, and we'll talk about what that is. Basically, row echelon form is this. In a 2 by 2 matrix, you're going to see I have this diagonal of 1s. And anything below each of the 1 is going to be a 0. That's what it's going to look like when it's done. I want it to look like that when it's finished. So I would do these row operations until I make it look like that. So let's have a look with this system of equations. Now we've already done the augmented matrix for this, so I'm just going to rewrite the augmented matrix at this point. Now the procedure for doing this, you could do any of these things at any time, but here's the deal. Typically, when I go back to these steps that we mentioned before, these two, the method and the procedure that I use, these are the ones I use to establish my ones. This is the one I use to establish my zeros. Occasionally, I might be able to use number 1 to establish a zero somewhere, but it's very rare. The other thing we want to keep in mind when we do this, I put a nice big star here. When we do these row operations on an augmented matrix, whether it's getting it to row echelon form or what we're going to talk about eventually, reduced row echelon form, I would like to establish the ones first and then the zeros in each column. So it seems kind of weird. We're going to use row operations and focus on the rows, but we want to be transforming each column one at a time. So that means if I'm trying to get into, say, a situation with a 3x3 matrix where I have this kind of setup, I'd want to establish this column first. I would establish the 1 first and then get the 2 zeros, establish this 1 next and get its 0, establish this 1 last, and then I'd have it in my row echelon form. So that means that if I follow that general guideline, the very first thing that I want to change here is I want to change this into a 1. So I have to figure out, well, again, how am I going to do that? Well, I could, add some multiple of the row below, and that's not going to cause a difference here. But the simplest way would probably be to take 1/2 of row 1. I cannot just multiply one number in a row. I had to change an entire row in some way. And so what this becomes is 1, 3/2, 5/2, and I didn't do anything to row 2 yet. So I'm good. The next thing I want to do, maybe use a slightly lighter color here, is I want to establish the 0 here. Well, I'm not going to be able to multiply or divide to get to that 0. Certainly doing a row swap is not going to put a 0 down there because I only have a 1 in the same position, in the first position on this top equation. So I have to figure out that when I do my row operation, row 2, I'm going to subtract 4 times row 1. Now we said add 2 rows together or add a multiple. Remember, subtracting 4 times row 1 is like adding a -4 times row 1. And so when I do that, row 1 is going to be left alone. I'm not transforming row 1, I'm just going to use a multiple of it and add it to row 2 to transform it. And so if I do 4 minus 4 times 1, it gives me the 0 here. It should, that's what I wanted there. -5 minus 4 times 3/2 will end up giving me a -11. -1 minus 4 times 5/2 will also give me a -11. So I got this column all taken care of. If I keep following and doing the steps the way I transcribed, find my 1 first, establish that, then establish the zeros, then anything I do from here on out should not change the 1 and 0 I have in this first column. A common mistake that students do is that they start doing and defining row operations that are perfectly legal to do. They're not wrong in doing the row operation. At least they're doing the row operation correctly. It's just that they end up undoing what they had previously established. And if you don't have those 1s and 0s where they're supposed to be, and if you establish the 0 where it needed to be, and then you do the next step and it gets rid of the 0, it's basically counterproductive. So the next thing I'm going to do, in the last row operation I really have to do to get this in row echelon form, is I'm going to do -1/11 of row 2. I could also say divide by it, but the same thing. So 1, 3 halves, 5 halves is left alone. 0 times negative 1 over 11 is still 0. That didn't change. Negative 1/11 times negative 11 is going to give me 1. And of course, I'm going to get a 1 over here as well. So I have this in row echelon form. Now, what does this mean? Well, going back to when we wrote these in augmented form, remember, this is my X column, this is my Y column, this is my result column. And each one of these had an X column, a Y column, and a result column. They got changed by doing these row operations. And so I have that going on down here. This row right here is telling me that if I have 0 X's plus 1 Y, that should equal 1, or simplistically, Y equals 1. This row, and I would usually start from the bottom row and work my way to the top. So if I had more rows, because it was a 3 by 3, I would start bottom, work my way to the top. This is saying that 1x plus 3 halves y equals 5 halves. Now knowing that y is 1, x plus 3 halves equals 5 halves. Subtracting 3 halves from both sides, I get x equals 2 halves, which also equals 1. So I could say for this that the solution is 1, 1. So here I'm using a very specific procedure and following that procedure through where I don't have to make decisions about x's and y's and what I should eliminate, which method should I use. I want to establish my column of 1 and 0s each way through, and that's going to help me figure out, how to do the rest of it. How to get to the point where I can start solving this equation or system. So going on to part B, this augmented matrix was written as, the first one I'm going to do, now again, I want to establish the 1, which should go right here. I always do the 1, establish the 1 first for a column. So I'm going to handle column 1 first. And so my row operation, I want to turn that 2 into a 1 somehow. The easiest way to do that is I'm just going to take half of row 1. Which means that row 2 and row 3 are left alone. Half of row 1, half of 2 is 1. Half of negative 1 is a negative 1 half. Half of 4 is 2. Half of 12 is 6. So that's what I've transformed this into. Now I want to establish my zeros here and here. I'm going to indicate 2 row operations at the same time because I'm going to do similar things to get my zeros. It also saves some space. Row 2, I'm going to subtract 4 times row 1. Because if we think about it, 4 minus 4 times 1, and that's why I always choose the one that has a 1 in it. Because if I choose the one that has a 1 in it, it's really easy to figure out what I need to multiply the row by to get the number I need to subtract or add to the number. For row 3, I want to get rid of that negative 8 and make it 0, so I'm going to add 8 times row 1 because I want to do 8 times that 1 I have in row 1. So for this one here, row 1 is the only thing that's left alone here. If I do 4 minus 4 times 1, I get 0. That's what I wanted. 3 minus 4 times negative 2 gives me a 5. Because that ends up becoming 3 minus negative 2, which is 3 plus 2. Negative 1 minus 4 times 2, well, negative 1 minus 8 is negative 9. 3 minus 4 times 6, well, 4 times 6 is 24. 3 minus 24 is a negative 21. Row 3, negative 8 plus 8 times 1 is 0. 0 plus 8 times negative 1 half would give me a negative 4. 2 plus 8 times 2, that's going to be 2 plus 16, that's 18. Negative 2 plus 8 times 6, well, 8 times 6 is 48, and negative 2 plus that is going to give me 46. So that's what I transported into. Now again, if I follow these steps the way that I've been doing, establish the 1 first and get the zeros in my column second, this column should remain unchanged as I go through the rest of this. That's important. Again, I could be doing correct row operations or legal row operations, but if I'm doing the wrong, if I'm not doing them in the right order, I could be undoing things I had done before and not get any closer to getting this in row echelon form. So now, the next thing I want to do is I'm going to go to column 2, and I want to establish the 1 here. That's where the 1 should go in the row echelon form, right? It should be a diagonal of 1s. So the row operation I'm going to need to do is I'm going to need to do 1/5 of row 2, or basically divide row 2 by 5. Which means when I do this row operation, the current row 1 is going to be left unchanged. The current row 3 is going to be left unchanged. It's just going to be row 2 that gets changed. So the 0 I had divided by 5 is still going to be 0. So that nothing happens there. 5 divided by 5 is going to give me the 1 I wanted. That's what I wanted there. Negative 9 divided by 5, I'm just going to write it as negative 9/5. And negative 21 divided by 5 is going to be a negative 21/5. First of all, notice this column untouched. Didn't change anything. And I want that to happen. The next thing I want is this to become a 0. So the row operation I'm going to do for this is I'm going to do row 3 plus 4 times row 2, because that's where the 1 is. I mean, theoretically, I could do row 3 minus 8 times row 2. The problem is that would make the 0 down here no longer be a 0. So I'm best doing the row 2 here because I do have a 0 in that position and not a 1 in the first row, in the first column position. So that's why that this is done really strategically, and it should be done in that order so that you're not undoing the work you did at each column along the way. I'm only changing the third row with this, so okay, 0 plus 4 times what's in row 2, 0, is still going to be 0. Negative 4 plus 4 times 1 is going to give me the 0. 18 plus 4 times negative 9/5 is going to give me 54/5. And 46 plus 4 times negative 21/5 is going to give me 146/5. I'm not showing all the computations that were done. You should be able to establish those on your own, but that's what they end up being. I'm almost done. The last thing I need to do to get this in the row echelon form is that this has to become a 1. And so my row operation, I'll just move it over this way so it doesn't get too low, is going to be, I'm going to do 5 over 54, the reciprocal, times row 3. Which means that again, these two rows are going to be left alone. If I multiply this 0 by 5 over 54, I get nothing. If I multiply this by 0 by 5 over 54, I still get nothing. So the zeros I established still stay. Again, that's why I do this. I wanted these, I wanted what I had as far as the 1s and 0s go to remain unaltered from this point on. Because if they change and become anything else, then I don't have it in row echelon form, and that would cause me an issue. This becomes a 1, because 54/5 times 5/54 is 1. 146/5 times 5/54 becomes 146 over 54, which does simplify and becomes 73 over 27. So again, what this means is that this bottom equation means I have 0x plus 0y plus 1z equaling 73 over 27, which means z equals 73 over 27. No one's going to say that these are always going to be nice numbers, by the way. This equation here is the same thing as saying 0x plus y minus 9/5 z, which we know is 73 over 27, equals a negative 21 over 5. Of course, that doesn't really happen here, so y is going to equal negative 21 over 5 plus 9/5 times 73 over 27. And when I work that all out, y ends up being 2/3. And now I could either come up to here and do this one, or I could go up to one of the original equations. I'm going to choose to go with that because I have an equation here where if I just know what z is, I can figure out what x is. And so I mean, it's up to you. I mean, you could use this equation here, which is just another version of an equation that came about from elimination. And with these row operations, I'm performing the necessary operations that I'm making equivalent equations along the way. So I opted just to say, okay, well, 2 times z, which we established already to be 73 over 27 minus 8x equals a negative 2. Negative 8x equals negative 2 minus 2 times 73 over 27, which is a negative 200 over 27. And then dividing both sides by negative 8, I get 25 over 27. And so my solution is 25 over 27, 2/3, 73 over 27. When I do Gauss-Jordan elimination, I perform the exact same type of things as I did in the previous problems. The only thing that's different is that instead of stopping with just having zeros underneath these diagonals, I also have zeros on the top of those diagonals. The reason being is if I look at, say, for instance, the one on the far right here, which I would have an x column, a y column, a z column, a w column, whatever the variables are. This would tell me essentially that x equals a, y equals b, z equals c, and w equals d. Because I would have an equation that has, the coefficient of 1 for one of the variables, 0 for the others, and it's going to be equal to a number. So that means basically just that variable equals that number. So that represents a solution. So so basically once you look at a augmented matrix written in Gauss-Jordan elimination and it's in reduced row echelon form on the left, you have your solutions in front of you. That's really the only other benefit from it. It does take more row operations, which, as you've seen, can take their share of time. So, that's the drawback, is that you do have to do more steps, But I mean, it kind of takes the place of the steps that you would be doing to take the value you got for, say, Z, plug it in to find out what Y is, and then plug those two in to figure out what X is. But, whichever one you feel more comfortable with, at a certain point, I usually just stop with the Gauss elimination, get it down to just row echelon form, and then just use substitution the rest of the way. But I'm going to demonstrate how to do this in example 3. Okay, so if we're going to be using Gauss-Jordan elimination or anything else, we want to be able to first write this as an augmented matrix. That's important. So I'm going to write this as an augmented matrix. The top row, 2, 1, 1, -3. The second row has a couple of pitfalls in it. No, first of all, it's missing a z term, which means its coefficient is 0. I'll put the -17 over here already. It has the y term and then the x term, so these are not lined up. Now, you don't have to write a whole step of lining this up like I did in the previous example. I just have to recognize that, well, there's a 5 with the y, and there's a -1 with the x. Recognizing that as I write this out, I want to have an x column, a y column, a z column, and a result column. So as long as I'm aware of what variables have which coefficients, I don't have to rewrite the equation completely before I write the augmented matrix. And anything missing would be a 0. So like in row 3 as well, I don't have an x term, so I have no x's, 1 y, -4 z's, and that equals 13. So there is my augmented matrix. I chose, because I see, although it's a -1 right now, I do see a 1 involved in row 2, so I chose to swap row 1 and row 2. So I'm going to have -1, 5, 0 on my top row with the -17 following it, the 2, 1, 1, and -3. And of course, a 0, 1, and -4 equaling 13 is unchanged. I almost have my 1 in that position. If I just simply take row 1 now, the new row 1, and multiply it by -1, then I'm going to have 1, -5, 0, +17. And of course, the rest of this is unchanged because I didn't change anything in the other rows. So I established my 1. That means I want to establish zeros in these two spots. Well, lo and behold, I already have a 0 in the third row in that position. Great. That's what I wanted. So all I really need to do is make a change to turn the second row into an equation that has 0 as its x term as well. So I'm going to take row 2 and subtract away 2 times row 1, because 2 minus 2 times 1, 2 minus 2 times 1 is going to give me that 0 I need there. But I have to make sure I do that for all of the entire row. So space out a little bit more. 1, -5, 0 being 17, 0, 1, -4 being 13. Those aren't going to change. So again, 2 minus 2 times 1 is going to give me the 0 there. 1 minus 2 times -5 is going to become 1 plus 10. That's going to give me an 11. 1 minus 2 times 0 is still going to be 1. -3 minus 2 times 17. Well, 2 times 17 is 34. So -3 minus 34 gives me a -37. If I follow this procedure correctly, the rest of this procedure, I'm not going to have anything go on differently here. That's going to stay the same. So I'm going to do one more row operation at this point. I want to now establish the 1 that I had over here. Now I don't want to add a multiple of another row because that's not going to help me here. You know, unless I choose to do a multiple of row 3, that won't affect my 0 at all. But it's just easiest to say, okay, well, I have 11 there, so if I essentially take row 2 and I divide it by 11, or multiply by 111, so I'm going to get what I need there. So this column, well, first of all, row 1 and row 3 are not being affected by this row operation because it's only affecting row 2. 0 times 1/11 is still 0. So notice again, my column of 1s and 0s have remained unaltered. 11 times 1/11, 11 times 1/11 is going to give me the 1 I want. So 1 times 1/11 is going to give me 1 over 11. Negative 37 times 1/11 is going to give me a negative 37 over 11. And in many cases, you are going to get some pretty gnarly fractions along the way. Well, now what I want to do is I want to get a 0 here and a 0 here. I established my 1. And anything I do beyond this point should not change this one. Those two that I just highlighted in orange need to become zeros. So I'm going to define 2 row operations to accomplish that. I'm going to take row 1 and add 5 times row 2. The reason being is if I take negative 5 plus 5 times 1, that's going to become 0. I also want this 1 to become a 0, so I'm just going to take row 3 and subtract row 1 because this 1 minus that 1 is going to give me the 0 I want here. And so with that being the case, so as I go through and do these, so row 1 and row 3 are going to be the ones changed here. This row will remain unaltered. If I look at this first row operation, row 1 plus 5 times row 2, I'll have 1 plus 5 times 0. That's still 1 plus 0, that's 1. So that's still a 1. Negative 5 plus 5 times 1. That's the reason why I did this particular operation. It becomes a 0. 0 plus 5 times row 2, or 5 times 1/11, is going to give me a 5/11. I shouldn't have a 0 here. (17) plus 5 times negative 37 over 11 becomes 2 over 11. Again, I'm not showing all the computations. However, you're responsible for being able to do those computations yourself. So make sure you practice your computations and using your calculator and whatnot. They'll obviously be a little easier to calculate on the final where you don't have the calculator, but right now you do have the calculator at your disposal, so do make use of it. Now I'm going to work on row 3, so I'm using R3 minus R2. So if I take this 0 in R3 minus this 0 in R2, it's still 0. So as you can see, nothing happened to this column. It's still my 1 and 0s in that column where they were before. Of course, 1 in row 3 minus the 1 in row 2 is going to give me a 0, which is what I wanted there. Negative 4 minus 1/11 is going to give me a negative 45 over 11. And 13 minus a negative 37 over 11 is going to give me, it's going to give me a 180 over 11. One of the things about doing this elimination method, is you're going to sometimes get some really nasty fractions and decimals, dealing with denominators that you're not used to seeing. You're not going to have fourths and halves and things like that. You're going to have like sevenths and elevenths, but they eventually do most often go away. So let's start with now I have my first two columns established. Anything I do from here on out should not undo any of this. So as I now define my next row operation, I'm just going to bring it back over here. I want to make this into its 1. So I'll have my diagonal of 1s after this point. So I had to think, well, what would I do to make that a 1? That's not going to change anything else I have in row 3. I don't want these zeros to change in any way either. So the best thing I can do for this is just simply multiply by the reciprocal. I'm going to multiply row 3 by negative 11 over 45. Which means this row is not being touched. This row is not being touched. And now when I get to this row, 0 times a negative 11 over 45 for both of these is still going to give me zeros in those positions. Negative 11 45ths times negative 45 over 11 is going to give me the 1 here. That's what I wanted. 180 over 11 times negative 11 over 45 is going to give me a negative 4. So as you see again, nothing changed with these two. I've established my 1, and anything I do from here on out shouldn't change that either. So I had to think what I need to do to get the zeros in the last two places, namely here and here. So row 1, I'm going to subtract away 5/11ths, row 3, and row 2, I'm going to subtract away 1/11th of row 3. And when I do that operation, row 3 is going to be left untouched. 1 minus 5/11ths of that 0 is going to be 1 minus 0. It's still going to be 1. 0 minus 5/11ths of row 3. I have 0 minus 5/11ths of 0. It's going to still be 0. 5/11ths minus 5/11ths times 1 is going to give me the 0 here, which is what I wanted. 2/11ths minus 5/11ths times negative 4 ends up giving me a positive 2. Second row, this 0 minus 1/11th of 0 is still going to give me 0. 1 minus 1/11th of 0 is going to give me still 1. 1/11th minus 1/11th times 1 is going to give me the 0 I want here. Negative 37 over 11 minus 1/11th of negative 4 gives me a negative 3. And so what these equations are telling me now is that, again, I have 1x plus no y's plus no z's equaling 2, which basically means that x equals 2. This one's saying I have no x's, 1 y, no z's equaling negative 3, which basically means y equals negative 3. And 0 x's plus 0 y's plus 1 z equals negative 4, which basically means that z equals negative 4. So our solution is 2, negative 3, negative 4. And that also brings me to the end of this particular video. If you have any further questions, please make sure to bring them up in class or come and see me during my office hours. Until I see you in one of those places or until our next video, I will see you around. Have a good day.